So concentration is also something that we can quantify. We have qualitative descriptions, dilute or concentrated. Those are relative terms. Dilute means there's a small quantity of solute relative to the amount of solvent. Concentrated means there's a lot of solute relative to the amount of solvent. And there's a whole bunch of different solution concentration units. And why are there so many? They are useful in different fields. Depends on what kind of units you're using for other things. It also depends on how much stuff is in the water, how concentrated or how diluted it is. Down here, things like parts per billion, that's what you might see in the water report that the city sends out. And it tells you how many parts per million or parts per billion these various things are in the city's tap water. So molarity is one we've been using. That's the amount of solute in moles divided by the volume in liters, so that's the same. Molality, which is, so close to molarity, it's just that one letter different, and it's a lowercase m, italicized. I really don't like this unit, but it's what it is. This is, again, the amount of solute in moles, but the difference here is now we're looking at the mass of the solvent in kilograms. We've got mole fraction, moles of solute divided by total number of moles, similar to the mole fraction of gases. You can also talk about mole percent. Take that mole fraction and multiply by 100. Parts by mass. This is the mass of the solute divided by the mass of the solution times a multiplication factor. So if we're talking about percent by mass, we multiply by 100. If we're talking about parts per million, we multiply by 1,000,000. Parts per billion, multiply by 1,000,000,000. You can also look at parts by volume, where you're looking at the volumes of the solute in the solution. So here, the volume of the solution is the volume of the solute and the solvent together. Here, the mass of the solution is the mass of the solvent plus the solute. So this one's review. We've talked about molarity and we've made solutions. Molarity is actually somewhat temperature dependent because the volume of the solution depends a little bit on the temperature. Okay, so the volume will get slightly larger at higher temperatures, meaning that the molarity will decrease. Most of the time, it doesn't matter, but there are situations where it does matter. And in those situations, you want to use molality, because here the mass of the solvent is not temperature dependent. So molality will be constant over a wide range of temperatures. Again, amount of solute in moles divided by mass of solvent in kilograms. Parts by mass, parts by volume. It's the part over the whole. Here the part is the solute divided by the whole thing times a factor. Remember that percent means per 100, so we're multiplying by 100. And we can take these percents and make them into useful conversion factors by looking at what this means. Percent, so 14% means 14 grams per 100 grams of the whole thing. If we're talking about parts per billion, 15 parts per billion by mass means 15 grams of solute per billion grams of solution. And this unit of mass here, you can use any unit of mass that you want as long as you use the same unit for the top and the bottom. Parts by volume, so 22% ethanol by volume, 22 milliliters of ethanol per 100 milliliters of solution. Or you could say 22 liters per 100 liters. Okay. What mass of sucrose in grams is contained in 355 milliliters, 12 ounces, of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. So a problem like this combines understanding the definitions of the different concentration units and then some dimensional analysis. So we will apply the same strategy that we've used before, and we'll highlight the numbers. So we've got 155 milliliters. The 12 ounces is really just to give you an idea of how big it is, because a 12-ounce can of soda is like kind of normal, right? That's why they picked 355 milliliters. So this is just an aside. That's not a number that we need to use. We've got 11.5% sucrose by mass, and we have a density here. And then we look at what are they asking? Mass of sucrose in grams. If you are calculating a concentration, just like if you were calculating a density, then you use the equation. But anything else, you're using the concentration as a conversion unit. So let's write these things down. I've got 355 milliliters of soft drink. I'm just going to call that soda. Because we have mass of solution and solute and solvent, we need to specify what these things are. So that's the volume of the soda, the solution. And then it says 11.5% sucrose. It's like, well, which is easier, C12H22O11, or I think sucrose is easier? By mass. So what does that mean? 11.5 grams per 100 grams. So that many grams of sucrose per 100 grams of the solution, which we're identifying as the soda. And then we have a density, 1.04 grams per milliliter. Is that the density of sucrose or water or the soda? That's the density of the soda, right? So that's grams of soda per milliliter of soda. So two of these things, numbers that they gave me, have per units, right? This per that. So this looks like a great conversion factor, and so does this one. This is just a single unit, milliliters. That's not going to be a conversion factor. So that's the one we're starting with. So we're going to convert milliliters of soda into something, to something, to something, and we're going to end up with grams of sucrose. Well, what can we convert milliliters of soda into? Grams of soda, right? How can we convert grams of soda to grams of sucrose? This percent, right? So it turns out I didn't need all that space. Let's just bring this guy over here. So 2 steps. So I'll start with my 355 milliliters of soda. And I've got 2 steps, so I have 2 fractions. The first one is I'm going to grams of soda. And the next one, I'm going to grams of sucrose. So I bring the previous unit down. And of course, this is not the only way to solve this problem. But we're just using a pattern that we have already learned, and it's just so useful for so many things in chemistry. So I'm just canceling the units out, and then I look at my numbers here, 11.5 grams of sucrose per 100 grams of soda. So that goes over here. And the density here is grams of soda, 1.04 per milliliter of soda. If you're still a little shaky on dimensional analysis, it's not too late to benefit from figuring it out. So then we use the calculator, 355 times 1.04 times 11.5 divided by 100. Should have three significant figures here. So 42.5 grams of sucrose in 1 can of soda. Any questions? If this was parts per million or parts per billion, the only thing different is that this number would not be 100, it'd be a million or a billion. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 ppb, parts per billion, by mass. What volume of this water contains 5.00 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1 gram per milliliter. So we've got 15 parts per billion by mass. We've got 5 times 10 to the 2 milligrams of chlorobenzene, and we have this density. And then we're asked what volume of water. So 15 ppb chlorobenzene. I'm going to call chlorobenzene CB for short. Whoops. So what does 15 parts per billion mean by mass? 15 grams per billion grams. Whoops, that's million. Billion grams. So that's the chlorobenzene. And then I've got 5.00 times 10 to the 2 milligrams of chlorobenzene, and I've got the density 1.00 grams per milliliter, and that's the density of the water. One of these units cannot be used as a conversion factor. Which one? This one, right? There's no fraction. There's no this per that. So that's what I'm going to start with. And I want to end up with volume of water. Well, it doesn't say, doesn't specify, does it, what the volume unit is. So let's say milliliters. We'll go to milliliters of water. So here I've got milligrams, and I don't have anything else that has milligrams in it. I've got grams. So we should probably take this to grams of chlorobenzene. And when we have grams of chlorobenzene, we can convert it to what? Grams of water. And then this density allows us to convert from grams of water to milliliters of water. I'm going to convert that to grams. I'm going to convert that to grams of water. And then I'm going to convert that to milliliters of water. So this is grams of chlorobenzene related to grams of water. So that's what I need here in the middle. 1 billion grams of water, it's a lot of water, is going to equal 15 grams of chlorobenzene. Density is the density of water. So the water is 1.00 grams per milliliter. And then the milligrams to grams conversion, I'm going to look at my prefix here, milli. Remember those? You're supposed to still remember those. Milli stands for times 10 to the minus 3. So if I have 1 milligram, I have 1 times 10 to the minus 3 grams. 5EE2 times 1 EE negative 3 times 1 EE9 divided by 15 times 1 over 1. And I'm getting a heck of a lot of 3's. So I'm going to put this into scientific notation so I don't have to count them all. Probably 2 sig figs here. So 3.3 times 10 to the 7th milliliters. It's a really big number, so maybe liters would have been a better unit, but this works. Any questions? So 3.3 times 10 to the 4th liters, same thing. So mole fraction and mole percent are closely related to each other. And this is that Greek letter chi again. So the mole fraction of the solute is the amount of the solute in moles divided by the total number of moles. So that's going to be the solute plus the solvent. If you want mole percent, you take the fraction, you multiply by 100. This one. Okay, we can do this. We can do this. The solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So here, we're calculating the concentration. So we are going to use the equations for the concentrations. Right? So molarity is equal to moles of solute, here sucrose, per liter of solution. Mole fraction is moles of sucrose divided by total moles. So that's moles of sucrose plus moles of solution. Molality, moles of sucrose per kilogram of solvent. I always had a hard time remembering that one. A kilogram is 1,000 grams. A liter is 1,000 milliliters. So if you have a kilogram of water, that's a liter of water. So this definition is going to give us a number very close to the molarity of the solution, because moles per kilogram of solvent, well, the kilogram of solvent is very close to the liters of solution, if that helps you. Mole percent, this one's easy. We're going to calculate the mole fraction and we multiply by 100. Percent by mass, grams of sucrose divided by grams of solution times 100. So we don't have to do these in alphabetical order. I'm looking at the last one and thinking grams of sucrose, well, they gave me grams of sucrose. And grams of solution, well, here's kilograms of water. So I could find the mass of the solution pretty easily. So 50.4 grams of sucrose So down here, I have 50.4 grams of the sucrose plus 0.332 kilograms of water. Is that going to be 0.000332 grams or 332 grams? It's going to be 332 grams. Just be careful when you're dividing by those numbers that are added. So 50.4 divided by, use your parentheses, 50.4 plus 332 equals times 100. Well, something clearly went wrong. I got 1,300. Okay, let's try that again. 50.4. I must have multiplied by 1,000. It's 13. So 13.2% by mass. The rest of these are all going to need moles of sucrose, so we'll have to calculate that. 50.4 grams of sucrose, and we need to calculate the molar mass. So we have 12 times 12.01 plus 22 times 1.008 plus 11 times 16. 342.296. So 50.4 divided by 342.296. 0.14724 moles of sucrose. So I guess we'll start with A then. So there's our moles of sucrose, 0.14724 moles, divided by the volume of the solution. Yeah, so we have 355 milliliters, so that would be 0.355 liters. So 0.41476, so 0.415 moles per liter. Molality, again, we're going to use that 0.14724 moles of sucrose, but now we're going to divide by, I'm sorry, we're doing mole fraction next. we're going to divide by the moles of sucrose plus the moles of solution. So we need to find the moles of water. So it's 332 grams of water times 1 mole over 18.02 grams. .424 moles. So 0.14724 divided by 0.14724 plus 18.424 0.0072928, and we will end up with 3 figures. 0.00793 is the mole fraction. Well, I'm going to skip down to mole percent. So this is just the mole fraction. Times 100. So 0.793%. The percent by mass is much larger than the mole percent. And here, the molality, we've got the moles of sucrose divided by the kilograms of solution, which was given up at the top there. Sorry, not solution, solvent. One, 4,724 divided by 0.332. 0.443. And that is moles per kilogram, or 0.443, lowercase italicized m. So the molarity and the molality are similar in number. Any questions? That probably seemed rather tedious. I've done it a zillion times, and I get to do it again tomorrow afternoon. Yes?
So for molality, it'll be different than molarity when it's like 30% of the solute and the solvent is kind of similar in weight, then that's going to be different, right?
Well, we're almost always talking about aqueous solutions. And so the molarity and the molality will generally be real similar because molarity, like a 2 molar solution is pretty high concentration for most things. And so the amount of moles per kilogram, it's going to be about the same. The amount of stuff you put in the solution doesn't affect its volume very much.
Okay.
Yeah, good question. Anybody else?